Section 7.2 Integration by parts. Integration by part is a procedure based on reversing the product rule of differentiation. We present this section not only as a technique of integration, but also as a procedure that is necessary in a variety of useful applications. Integration by parts formula. Recall the formula for differentiation of a product. If u and v are differentiable functions, then duv equals u dv plus v du. Integrate both sides of this equation to find the formula for integration by parts. If we rewrite the last equation, we obtain the formula summarized in the following box. We take an example. Find the integral of x sin x. To use integration by parts, we must choose u and v so that the new integral is easier to integrate than the original. In this example, let u be x, then du be dx. The remaining part, sin x dx, is dv, so v is minus cosine x. To find the integral of uv, we take the difference of uv and the integral of v du, so the integral of x sin x dx equals minus x cosine x minus the integral of minus cosine x dx. The last integral equals sin x plus c, so the result is minus x cosine x plus sin x plus c. You can check your work with integration by parts by differentiating using software or using the integration table. Repeated use of integration by parts. Sometimes integration by parts must be applied several times to find a given integral. The idea is to let u be parts that gets better when we take derivative. For example, x to the nth log n x, and let dv be the part that we can integrate, such as sin x, cosine x, exponential x. We take an example. Find the integral of x squared exponential phi x. Let u be x squared, then du is 2x dx. The remaining part, exponential phi x dx, is dv, so v equals 1/5 exponential phi x. Applying the formula of integration by parts gives 1/5 x squared exponential phi x minus the integral of 2/5 x exponential phi x. The integral on the right must also be found by integration by parts. This time, let u be x, then du is dx. dv is exponential phi x, so v equals 1/5 exponential phi x. Using the formula for integration by parts in the above equality, use the result for the initial integral. This result can be checked with formula 185 in the appendix. We take another example. Find the integral of x cubed sin x. There is a simple way to keep track when we do integration by parts several times. We write in the first column the function you choose as u, taking derivatives of this function until you get 0. In the second column, write the part that you choose as dv without dx. Take the integral of this function to the same level as the first column where the derivative is 0. Now, take the product of the first term in the derivative column with the second term in the integral column, the second term in the derivative column with the third term in the integral column, etc. Notice that this product has the signs beginning from plus and alternate between plus and minus. So the integral equals to x cubed multiplied by minus cosine x minus 3x squared multiplied by minus sin x plus 6x cosine x minus 6 sin x plus c. You can compare with formula 134 in the appendix. In the following example, it is necessary to apply integration by parts more than once, but as you will see, when we do so a second time, we return to the original integral. Integrate exponential 3x cosine x. Let u be exponential 3x, then du equals 3 exponential 3x dx. The other part is dv equals cosine x dx, so v is sine x. The initial integral is the difference between exponential 3x sine x and the integral of 3 exponential 3x sine x. Applying integration by parts again for the integral on the right, let u be exponential 3x, then du is 3 exponential 3x dx. The other part is dv equals sine x dx, so v is minus cosine x. Insert the results in the formula above gives R. Notice that the integrals in the box are the same. To find it, solve the equation and remember to add c in the final result. Check with formula 193 in the appendix. In the following example, the differentiable part is the entire integrand. Find the integral of log n x. Let u be log n x, then du is 1 over x dx. The remaining part, dv, is dx, so v equals x. Applying the formula for integration by parts gives x log n x minus the integral of dx. Integrating dx gives x and add the constant c to obtain the result. Check appendix for formula 196. Definite integration by parts. The integration by parts formula can be used for definite integrals. The formula for definite integrals is the same as the formula for indefinite integrals, where the first term after the equal sign has been evaluated at the appropriate limits of integration. This is illustrated by the following example. Find the integral of inverse tangent x from 0 to 1. Let u be inverse tangent x, then du is 1 over 1 plus x squared dx. dv equals dx, so v equals x. Applying the formula for integration by parts gives x inverse tangent of x minus the integral of x over 1 plus x squared dx. Using substitution for the integral on the right to get 1/2 log n of 1 plus x squared. To find the definite integral, evaluate the antiderivative at the limits and take the difference. The result is pi over 4 minus 1/2 log n 2. Check appendix for formula 180. This is the end of section 7.2. Thanks for watching.